Thanks for the opportunity to present some of our work on pattern formation. Let me just tell you what you're looking at here in case you don't know. That's not tiger stripes. What that is a picture of, it's just take an image grabbed from Google Maps from the Horn of Africa near the Somalia-Ethiopia border. And what you're seeing are dark bands which represent vegetation, and then these orange bands that correspond to bare soil. So this is the pattern formation problem I'm interested in. This phenomena was first reported in 1950, and it was came to light by people doing aerial surveys of the land. So this is one on the left is from this paper by McFadden. And the main thing, so here again, we see the stripes of vegetation and the bare soil. And the things I want to point out here are the scale bar. So it's a kilometer. So these bands are separated by, say, 100 meters or so. And the other thing I'll point out is that there's this arrow, and that arrow is indicating the downslope direction. So these bands are oriented transverse to the downslope direction. If you were on the ground, like this woman over here on the right, she's standing near the edge of one of these vegetation bands. So you can see the bare soil region. And what I want to point out is that the band is a mature community. It's got grasses and shrubs and even some trees within it. The other thing I want to mention is that this is a phenomena associated with dryland ecosystems. So these are ecosystems for which water is the limiting resource. And the drylands comprise about 40% of the terrestrial globe. And the other thing I want to point out is that when this term drylands was introduced, and it was not only that these were water limited ecosystems, but that the water inputs are infrequent, discrete, and unpredictable. And so a lot of the goal of what we're doing right now is to try to capture some of those aspects of drylands within our modeling framework. Okay, so here's an outline of my talk. The first part, I'll just give you a little bit of background on this phenomena in case you weren't aware of it before today. And I also, as somebody working on pattern formation, want to put forth some, basic pattern formation questions that drive what we're doing. Then the middle part of the talk, which is the bulk of it, will be to describe the model that we're currently developing and some of the kind of numerical experiments that we're doing with that. And then finally, at the end, I want to turn to some other people's works and make some comparisons and think a little bit about where we might be headed with this research. Okay, so I said that this is a dryland phenomena, but it takes more than just being an arid or semi-arid ecosystem. This isn't something that's a phenomena that's covering 40% of the globe. There was this interesting paper from this Belgian group, and what they did in it is that they took from the literature the descriptions of this and the locations and fed those along with global data sets into ecological niche machine learning algorithm, and tried to figure out from where they had been sightings of this, where one might want to look further. So they had a lot of things, but I think some of the main takeaways I want to highlight is that I associate this with regions that are not only dry, but hot and flat. And there's probably additional things as well, but I want to just highlight those three. So in this figure, I'm showing one of the images from that paper by De Blauwe et al., where they did this. And so you can see they're looking at a region in North America, a region in Africa, and a region in Australia where these patterns were observed. If you can see these blue splotches, those were the ones that they got from the literature, and then green are like new locations that emerged from their study. And if we take their splotches and overlay them on a climate map, which is what we've done here. These black splotches are just translating theirs there. So you can see that the sightings sort of coincide with these red regions and these orange regions. And in that climate classification, those are the warm arid and warm semi-arid climates. Okay, so I have this additional thing is that I claim it should be flat. And there are lots of indicators that you really don't want there to be much of a slope to the terrain, like definitely less than say 2% slope. But I want to highlight again another one of these studies from this Belgian group that I like a lot. They focused on this region in Sudan where there is a large aridity gradient as you go from the northern regions, which are more arid, to the southern regions of Sudan. And one of the things that they wanted to focus on was these predictions that were coming out of models. They're models that they were looking at, but also a wide variety of models that sort of indicated the same kind of story, which is the following. Let me just focus on the bottom part of this, where I say flat terrain patterns. The vertical axis is a slope, but let me just focus on the flat terrain patterns, and I'm going to increase aridity. So the predictions from these models were that if it wasn't very arid, you could have uniform vegetation coverage, and if it's too arid, you've got bare soil. And in between, you go through this sequence of patterns. So it goes from uniform coverage to what they call a gap pattern, labyrinthine pattern, and then spot pattern, and then ultimate collapse to the desert state. If there's a slope, though, then these patterns that are associated with the flat terrain get taken over by what are called the banded patterns. And everything that I'm going to be doing in the model I talk about today is focused on these banded patterns. So what they did in this study is it was associated with this red rectangle in Sudan, and you can see the precipitation levels, going from 200 millimeters a year to say 600 millimeters per year. And so they look in that region and they built a classifier for the pattern. So they, at each location, they decide, is there a vegetation pattern or not? And if it's a vegetation pattern, they classify it according to whether it's spot, labyrinthine, gapped, or banded. And indeed, what they find is that as it becomes, if you go from the wetter region to the drier region, you go through from these gapped patterns to the labyrinthine to the spotted pattern. So that's some evidence that the models are doing something reasonable. They're highly conceptual models, but they seem to always give the same story, the variety of them. The other thing is that there's this red region, which is the banded pattern, which is my focus today. And I just want to show you another figure from that. So this is showing this rectangle here labeled with the letter E. And what they've done is put in, that rectangle, whether it's banded, gapped, or this banded again. And then they've overlaid an image of it on an elevation map. And so you can see that the banded patterns are associated with the sloped regions and the gap patterns with the flat one. But what I want to point out is that the scales are very different here. In the horizontal, we're looking at a region that's 6 kilometers by 1 kilometer. And if you look at the elevation, there's at most a gain over this of about 10 meters. So this slope is like 5 meters over a kilometer. So it's like 0.5% grade, say. And I put in a little triangle here. I hope you can see that this little triangle is has that 0.5% grade. So I would say that these patterns are appearing in flat regions, and it's just that the some of it's even flatter and gives you these patterns. So I'm going to be focusing on these slope terrain patterns. Okay, the next thing I want to do is talk a little bit about timescales, because that's one of the challenges of this problem. Okay, so this is again an image from an old paper from 1965 by Hemming, and he was doing ground-based studies. So he was there for a long period of time, maybe years, studying this phenomena. And he has these beautiful hand drawings of one of these vegetation bands. And one of the observations he makes is that there is colonization going on at the leading edge of the band. So there's some recruitment going on at the top edge of this band, top meaning at the upslope direction. And at the downhill side, there's die-off going on. And he makes the observation that these vegetation arcs are actually migrating upslope at a rate that he observes about 15 to 30 centimeters per year. This arc is 18 meters wide, and so it would take it, say, on the order of 60 to 120 years is his projection for it to move the, one vegetation arc's width. And you can actually go now and check those predictions. So this is image from one of our studies where we took one of those 1950 photographs, aerial survey photographs, and got the corresponding one from, a high satellite data. Okay, so here's the 2006 one, and you can go ahead and align these on, geological features within this. You don't want to align it on the bands, but you can go ahead and align these two images very carefully. And what you find is that indeed you can just match up the bands from 1952 with the ones from 2006. This is a false color image of this, and you can see that in fact the band did move about an arc's width in that 50 some years. Okay, so the dynamics of the vegetation is very slow. And I want to contrast that with the dynamics associated with the water. This is a phenomena that's in response to these rainstorms. And if you look at that, so this is from another ground-based study in Mexico where they had these bands, and they looked over the course of the year, 1985. On the top is sort of these rain events, these discrete, infrequent events, just indicated as these spikes here. And what they did was they looked in a band in the neighboring bare soil regions, and they looked at the soil moisture content. And there's two things I want to point out here. One is that is this vegetation water feedback. There's a positive feedback here. So you can see that in the vegetated zones, there's just enormous infiltration compared to the bare soil region. So the biomass ends up recruiting more of the water to it, and then it can grow more. So that's the positive feedback. And then the other thing I want to point out is that they were making, I think it was like weekly measurements of the soil moisture, and you can see that there's just, what we think of as just sort of an instantaneous jump in the soil moisture content when the rainstorm happens. And then say over the weeks that follow, there's some kind of decay in that if it's dry. Okay, so there's that's a challenge of this problem, is that the feedbacks are really happening on this very fast time scale, but what we typically view is the biomass, which is evolving very, very slowly. Okay, so I now have one last bit of background information, which is to think about what might be interesting to investigate here for the pattern formation problem. And I think the most basic question we might ask is, we know there's not enough rainfall to get uniform vegetation coverage. Okay, so we might expect that the vegetation is going to be patchy, and say we're in those banded patches, what is deciding the spacing? So that would be the most basic question I might want to be able to answer. And I want to contrast that with other pattern formation problems that I've investigated in the past, and what sets the periodicity in those. Okay, so there's things like Rayleigh-Benard convection, where you have a layer of fluid that ends up forming these convective rolls, and there the spacing of the convective rolls is set by the physical scale of the depth of the fluid layer. So that's one example. Another system that I've looked at quite a bit are these Faraday waves. So that's where you have a layer of fluid and you're subjecting it to a vertical vibration. And there what the set, so you can see these beautiful arrays of peaks on the surface of this fluid that are excited by this vibration. And the way that the spacing is determined in this case is that it's a subharmonic response to the vibration frequency. So you can take that subharmonic frequency and plug it into the gravity capillary wave dispersion relation and get a length scale out from that. So it's a kind of resonance phenomena that's going on here. And a lot of the last example I have is for Turing patterns. So this dates back to work of Alan Turing that proposed this mechanism. And a lot of times people invoke Turing's name when they start talking about pattern formation. And it's an interesting phenomena where the length scale is just some emergent feature. It's typically talked about in a setting of an activator chemical and an inhibitor chemical, and the activator diffuses more slowly than the inhibitor. And so the length scale depends on, in not necessarily a straightforward way, on reaction rates and the diffusion rates of this activator and inhibitor system. So it was actually hard for people to get these patterns in laboratory experiments because you needed this difference in diffusion rates, which typically doesn't happen in these chemical systems. So there was a clever experiment that finally observed this in 1991 by having the reactions take place in a gel. Okay, so those are different pattern forming systems with sort of different stories behind what's setting the wavelength. And I want to just go directly to a punchline or a claim I want to make. And this is a claim about based on our model, which I'm about to introduce. But I want to make the claim that the length scale might be estimated by the following, that it's determined by a typical overland distance that water would travel on the surface before it fully infiltrates into the soil. So if you say, okay, a typical storm depth of 1 centimeter, infiltration rate, centimeter an hour, flow speed, 100 meters per hour, and you put that all together, you get an estimate of around 100 meters. So it's sort of the right ballpark. This is very crude, but that's the story I want to put forth based on our model. So and I'll show you some evidence for that shortly. So I feel that it's I don't know whether I would say that this is like any of those previous ones. The interesting thing, and maybe it's because I spent a lot of time working on Faraday waves, is that maybe there is some kind of resonance going on, but in the system, and I'll explain that in a minute. Okay, so what are our goals here within this model? One goal is that I want to be able to capture the variability in storm depth. So I want some kind of model that I can do many realizations for simulations. And I want to be able to both capture these fast equal hydrological feedbacks, but also be thinking about what's going on with the biomass over decades or even centuries. And so those are the goals, sort of the constraints on the modeling. And the questions I'm particularly interested in, this first one relates to climate change. I just want to know what might happen if there are changes to things like typical storm strengths. Okay, so not just how much water is getting into the system, but how it's coming in, what might happen. And I'm also, based on these kind of like crude estimates, wondering the extent to which these vegetation patterns may arise under one kind of rainfall pattern, and to what extent are they perhaps sort of tuned to that rainfall pattern. So those are the questions. The specific model I'm going to move on to describe was developed in a collaboration I have with Puneet Gandhi. And this particular version of the model, we also worked with the University of Chicago undergraduate, Lily Liu. And so we have a preprint that we're about to release that's on this work. So that's it hasn't gone through peer review yet. However, it builds on an earlier model that we have published. So this was this is the model that we're adapting for the stochastic rainfall. And this came out of a collaboration again with Puneet Gandhi and another collaborator, Sarah Imes. And what we did was we were fortunate to get some help from a couple hydrologists or eco-hydrologists, Amilcare Poperato and Sarah Benetti. So they helped us with kind of trying to come up with something reasonable for the hydrological part of the modeling, and also like how do we choose parameters and things like that. This model follows surface water flow, soil water content, and biomass in a PDE setting. This choice of variables that we want to follow is very much in the spirit of earlier models. So there's this Rietkirk model. Rietkirk is a ecologist in the Netherlands. So they have a model that's of this type, and we borrowed a lot from them. And also Ehud Meron, who's a theoretical physicist in Israel. He has done a lot of work in this area and also has similar types of models. So, so again, just looking at these three fields, it's sort of the simplest framework we could come up with. And I want to point out a couple of differences between what we're trying to do and what was done in the past. One is that we want to take these earlier models. They really were thinking about the biomass timescale, so they're just put in the average precipitation. So they were sort of thinking about, yearly rather than individual storms. So we want to make this precipitation, rather than being a constant bifurcation parameter, just put it in some time dependence in that on the typical storm timescale. The other thing is that in this water transport term, we want to put in a feedback, which is the following, that when the water's flowing over land, if it's going over bare soil, it's going to be moving much more rapidly than if it's trying to travel through shrubs and grasses. Okay, so there's a feedback that the water is going to slow down when it gets to the rough parts of the surface, which are associated with the biomass. So those are two differences between our models and these other ones. And the other thing is that if you put in the parameters based on what the hydrologists tell you to do and non-dimensionalize the equations, there's a small parameter, which is that the infiltration time scale is much faster than the growth time scale. So in this kind of fast, slow framework, you see that the biomass evolves very slowly. The surface water that contribution is only on the fast time scale, and the soil moisture has elements on both time scales. Okay, so that was the model that we're now going to adapt for putting in some kind of stochastic rain inputs.
Mary, may I ask you,
sure.
In your equation before, what are so it's a velocity, it's a V of B and H is a velocity. So what is this velocity?
I will show you. So what we did was we wanted to put in surface roughness. So we have something that we put in like 1/1 plus eta B, where eta, it was like something like 20. So we wanted to have it like over the bare soil, it would be going at 1 velocity, and over the vegetated soil, it was going as like 10 times more slowly. Okay, so that's one thing. And then the H, well, we tried a couple of things. One was to neglect the H dependence, but what Sarah and Milkray would have liked is to have it go like h to the 2/3. Okay, does that help?
Yeah. So it includes a sign, I mean a direction in the
Oh,
motion?
yeah, sorry. Okay, yeah, thank you. Okay, let me slow down for a second. We're going to do this on one dimension.
Yeah.
Okay, and the velocity goes as the slope, the square root of the slope.
Okay,
So
yeah.
I'm going to
Right.
take it as a uniformly sloped
Okay,
terrain.
so it's downward the slope. Right?
It's going downward, right?
Okay.
Yeah. So
Okay.
the slope,
Yeah, yeah.
it's oriented, this velocity is going to be positive and it's sloped in the plus x direction.
Okay, thanks a lot.
Yeah, thank you for asking that. Okay, so I want to also tell you what kind of rainfall model we're going to put into this system. So this is reanalysis data from this region in Somalia that has these banded patterns. So this bottom plot is just showing this rainfall rate in centimeters per hour over a 5-year period. And if you collect each year, you can see that there's variability in the yearly rainfall. And then if you look collected into months, you can see that in this region, there's 2 rainy seasons per year. And there's some distribution of rainstorm strengths. Okay, so this histogram is just showing the strength of the rainfall in this centimeters per hour that it's, I think it's either centimeters per hour, centimeters per half hour that's available at this NASA website where Puneet gathered this data. So the way that we're going to model the storms is we're going to make them instantaneous pulses to the system. So we're not going to actually resolve the rainfall. We're just going to say there's instantaneously a storm came and it deposited water on the surface. We're going to take 2 rainy seasons per year. We're going to make them identical so that the sort of periodicity in our model is 6 months. So 2 equally spaced rainstorms of the same duration. We'll take the arrival times as a Poisson point process, and for the storm depths, we're going to take them as drawn from an exponential distribution. So I like to think of it, there's kind of 2 parameters here. One is average storm depth, and the other one is how much rainfall comes per year, like how many storms do we expect in a given rainy season. Okay, so here's the actual model, and I show more details. And this is simplified from that fast slow model, and I'll explain why we did that. But here's the way the model works. It's separated into a subsystem that applies when a storm is present, and another subsystem that applies when there's no rainfall coming in. So there's a wet season, a dry one, or wet instance. And so if we start with just this fast subsystem, we need as input to that, what is the biomass distribution? Because that's going to determine this infiltration rate at each location and the overland speed. Okay, so I'm now making this velocity only depend, once it's been non-dimensionalized, okay, it's only going to depend on the biomass at each location. The infiltration also only depends on the biomass. So these are the 2 feedbacks here in these parameters. This theta is a Heaviside step function. So basically we say, okay, the water's infiltrating as long as there's water on the surface, and then this fast system is done. So if you want to know how much water got deposited into the soil at each location, you have its infiltration rate, which depends on whether it's how much biomass is there, and then the length of time that there's water infiltrating. Okay, so that then gives you the updated soil moisture, and you feed that into this flow system, which is a reaction diffusion system of equations for soil moisture and biomass distribution. You run that until the next storm comes, and then you go back to this fast system. So that's the way that we're going to investigate this. Again, we're just doing it on a 1-dimensional domain with a uniform slope, and we're going to imagine that we're actually looking at sort of a middle portion of this slope, and we're going to apply periodic boundary conditions at the ends of our domains. So we're not considering like that we're at the top of the hill or the bottom of the hill, but just in the middle portion. Okay, I want to now just say a little bit more about this fast subsystem, because we really kept working to simplify it and simplify it and simplify it so we could get something that would be quick to solve, because we want to be able to run this for long periods of time with lots of different storm characteristics. So what we do is this equation is in the form that we can just use method of characteristics to solve it. So the idea is that we put in a pulse of water at the beginning of that's uniform on our domain. So think of it like this. Okay, instantaneously there's this distribution of water. Actually, if you look over here at these figures, here it is. There's the surface water height initially. And what we want to know is how does that get distributed into the soil? And that's shown in this bottom plot. And this is for this biomass distribution here. And the direction field shown in the background is what you get from using this method of characteristics on it. So the way that we actually do this is we think of these characteristics as being anchored at some location on our domain, and we follow them backwards. And what the amount of water that's going to infiltrate at that place depends on the, following these characteristics backwards and looking at the area of those between two of those, say, that is below that initial surface water height. So we can show that that's what you end up with here. So we turn this like redistribution into just simple integrations over this domain. Okay, so that's how we ended up with this model, is just trying to make something simple. The thing I will point out is that it does something reasonable here in that the water gets preferentially infiltrated into the soil in the region where the biomass is located. Okay, so here is a sort of typical simulation result that I can show you. Here on the left, it's just, this is 2 rainy seasons per year over 200 years for this simulation. And what we point out here is the largest storm in each year and the annual rainfall. And so we see this sort of spikiness there. And then these next 2 plots are space-time plots. So on the horizontal is our 1 kilometer long domain, and the vertical is the 2 centuries of the simulation. Our initial condition here was uniform vegetation with just a little bit of noise on top of that to trigger the pattern formation process. Again, this is the plus X is the uphill direction. The parameters were chosen on an assumption that the slope was about 0.5% and uniform. And so what you can see here, here's the soil water. We see it being preferentially infiltrated into the regions where there's biomass, and the waves, these sort of noisy band patterns, are in fact traveling in the uphill direction here. Okay, so that's typical simulation result. I want to turn now back to this claim that this spacing of these bands is somehow tuned to the typical storm height. And in particular that the claim was that the band spacing was related to how far water would flow down the surface before fully infiltrating. Okay, so here's one bit of evidence associated with this. So what's plotted on the bottom here is the biomass in the last year of the simulation. And we're showing both the maximum biomass and the minimum biomass, and then also the average over the course of the year. So we see these vegetation bands. And then what I want to point out is this top plot, actually. So what we do here is at each location on the domain, during each storm, we look at like, well, what is the furthest away that water was? And I want to look like how far did it possibly travel? So we look for that sort of longest distance of travel before it infiltrates at that location. Okay, and so there's three curves here. The two of them are associated with sort of the biggest storm and the smallest storm. And then in that year, there might be, tens of, a dozen storms. And so we could also look at their average. Okay, so that's this sort of more wiggly, jagged curve. And then overlaid on this, I put the wavelength associated with this. Okay, it's 1,000-meter domain, and there's I think there was six bands on that, so I get some characteristic spacing here, and that spacing is about twice this average distance of travel. Okay, so it's so that's one indication that that travel distance is somehow related to this spacing. The way that we started thinking about this actually came about by thinking about the pattern formation problem. And sort of the starting point of any pattern formation problem I might look at is that I would want to say like, well, when is the uniform state unstable to heterogeneous perturbations? Okay, so I don't know how to do that calculation in this stochastic setting, but what I could do is say, okay, let's not do stochastic rainfall. Let's just say that we have a rainy season and all of the rainstorms are identical. And so I'm just going to do a periodic rainfall input, and I linearize my equations about this uniform state. So I'm going to look at the response to perturbations of the form e to the ikx. Okay, so I'm just doing linear stability, and I can go ahead and compute the flow K multipliers for that linear stability problem that I'm calling lambda sub k. So we do this calculation. We do it as a function of k, and then also as a function of how much rain came into the system over the course of the year. Okay, so we had maybe pulse heights of some number of pulses, and we just increase how large they are to increase the mean annual precipitation. So what's plotted here is the leading flow K multiplier, the magnitude of it as a function of the mean annual precipitation, the perturbing wave number. And the red regions are associated with instability of flow K multiplier bigger than 1 in magnitude. The black curves are where the flow K multiplier is exactly 1, and then the stable regions are associated with blue. And so what totally surprised us when we went to do these calculations was this resonance tongue kind of character to it. And with this back of the envelope calculation was exactly what we did to figure out the spacing of these resonance tongues. So we could just, this white curve is just based on that crude estimate of how far would the water travel before infiltrating. There was something surprising that also came out of this. So there's two things, right? These flow K multipliers end up being complex, and if you plot their magnitude, that's what I was just talking about, you get this oscillation in it, where it's sort of, as you increase K, it's unstable, then stable, then unstable. But you could also look at the phase associated with these. So the phase is going to tell you whether in one period, is a phase increased or decreased, and that's going to tell you how the pattern, how the pattern travels, whether uphill or downhill. And so this was kind of troubling to us because we found that in these unstable regions, actually the waves could switch their travel distance, whether they're traveling uphill or downhill, but all the observations indicated uphill travel. So this is my last sort of pattern formation result. so what we did was we looked at simulations with periodic rainfall and also with stochastic rainfall. And in order to look at variations with the wave number K, what we did was we sort of shrunk our domain, and we're using periodic boundary conditions. So we just seeded it with a little bump on the domain. And so you can see at 200-meter size domain with periodic rainfall, we get this nice regular traveling wave traveling uphill, and the stochastic same thing. But if we shrunk the domain, suddenly we lost these traveling waves. They become, that's not what ends up happening, and we get this very weird pattern. But if we look at the stochastic one, it's just doing something very reasonable. And if we shrunk the domain even further, suddenly it starts traveling downhill. And however, that's not the case with the stochastic input. So there's just, even though this idealized rainfall model is giving us something kind of nonsensical, or, you know, it's doing what it's doing, but at any rate, the stochastic version does something that's always reasonable. Okay, so let me just turn to some simulation results. So one thing that we were interested in was collapse events. So we went to a region in our phase space where we had the desert state coexisting stably with pattern states, and we looked at the collapse of the ecosystem. So the collapse is signified by the biomass on the domain dropping below some threshold and staying below it for at least 10 years. Okay, so here's a collapse event. And we can ask ourselves, well, what in the rainfall, you know, what aspect of the rainfall might be associated with these collapse events? So what we did here was, this was for 200 trials. And this is on the left here, I'm showing just results from one trial. So this is the spatially averaged biomass in the domain. This red vertical line is indicating when we signified a collapse event where the biomass just decayed after that. And we can look over, you know, the time period in these 2-year windows, like what is the rainfall and what is the typical storm strength. And so what we find, putting this all together and sort of lining up all of the simulations, calling t = 0 is when the collapse happened, was that we did see that that was associated with a drop in the mean annual precipitation. I would have liked if we could say, oh, it's also associated with a change in the typical storm strength. That it is, but it's also associated with a change in the number of storms. So this is the kind of diagnostic we can look at associated with these collapse events. I'll just show you, we've done a number of experiments. This is one that Lily sort of spearheaded, where she looked at what happens if we change the length of the rainy season. So she kept the same, in fact, what she did was she had the exact same seeds for these. And so she would run it with one rainfall sequence and then just change the length of time over which that rainfall sequence happened. And she found that this typical collapse time increased if she increased the rainy season. In fact, this point is just saying there's not a rainy season, it's just raining year round. And so I just maybe make one reference to things that are inspiring some of these studies, is that there is this thing that they call the East African paradox, which is, I don't really think it seems like a paradox, but it's that there has been, you know, severe droughts in these regions associated with one of the rainy seasons over a 10-year period. And the paradox part is that the models, the big models, were predicting that there should be more rainfall, not less. And that when they looked at like what was causing this decrease, it was actually not a change in the intensity of the rains, but in the duration of that rainy season. Okay, I want to wrap up by just some comparisons with other studies. So here's one paper last year from Crompton and Thompson. So they were also interested in looking at dryland vegetation patterns under changes in storm characteristics. Their approach was had some similarities to ours in that they wanted to kind of do something for the overland flow and something different for the vegetation growth. They also based it off of a modified Rekirk model. But what they did for the fluid flow is they actually looked at these shallow water equations on this rough surface, so these St. Bernard equations that I alluded to, together with a Richards equation for infiltration. But what they say is, like, if they actually were to run this, it's too expensive. They're doing it on a two-dimensional domain, 200 meters by 100 meters. And basically, if they tried to have 632 storm events over, a decade or two, it would require 2 months of supercomputer time. So they've got to come up with some method to speed it up. And what their approach was to use was to build an emulator. So they use a machine learning technique to come up with some kind of statistical model for how the water should be distributed given the vegetation and the storm characteristics. So that was their approach. Here's one of their plots looking at the patterns. They don't use periodic boundary conditions. They're looking at storm duration. We don't have that in ours because we said the storms are instantaneous, but they did look at storm depth, and they see a similar thing to what we're seeing, which is that as the storm depth increases, the spacing between the bands increases. Okay, here's another point of comparison. This is from work of Max Rekirk and Arian Dolman's group. Rekirk is a ecologist, Dolman is a mathematician. They were looking at a very idealized vegetation pattern model that came from Klausmeier that has this uniform, this constant precipitation parameter A. And they could go ahead and do an analysis of these equations to get the stability of the nonlinear traveling wave states. So they've done that here. And what they did some experiments where they ramped the precipitation parameter down and then back up. And so they'd see this kind of coarsening go on as they decrease the amount of rain in the system, and then splitting events going back. With our model, we can do similar kinds of ramping experiments, but there's some interesting ones that we've tried. In this one here, we kept the mean annual precipitation the same over the course of the year throughout the simulation, but we changed the typical storm strength. So we went from it being like 0.5 centimeter to 2 centimeters, and then ramped it back down again. So you can see this, these sort of isolated splitting and collapse events or merging events, and that there's considerable hysteresis in this. I would love to be able to talk about this project, but I realize I'm running kind of low on time. But what this is old work, or not that old, but work with a former PhD student, Karna Gowda, and a collaborator, Sarah Imes, where Karna's idea was to go ahead and take those old photographs and get high resolution satellite data and to go ahead and match them up. And what he was able to do with this, and I just want to point out that this is possible, is you can look here at what's happening to the band width. Okay, so he could match them sort of one-to-one, these bands between the past and the present, and automate getting the width of the bands, in their, are they getting wider because of upslope colonization or retreat? And in this paper, he looks at changes in different regions and traces that to a correlation with signs of humans. In the disrupted regions, he sees a change in the band characteristics. And if there is no signs of humans, they seem to have persisted with the same widths. Okay, so let me just wrap up with my disclaimers and claims. So the disclaimers, we restricted to one dimension, uniform slope. The two-dimensional problem is much more interesting because you can get more interesting topography, and that's going to play, that variation in the topography is going to play an important role in figuring out catchment areas and redistribution of the surface water into the soil. The model we used is not what the hydrologists would use, and we use the pulse precipitation, the indications from that Crompton and Thompson papers that storm duration could matter. So what I'm interested in is whether the model is good enough for predicting trends. So I think that's going to rely on doing some more careful comparisons with more detailed models. We use periodic boundary conditions. It doesn't account for runoff losses. We didn't investigate anything related to soil type or vegetation type, and transport of biomass. So there's a bunch of things that we just held fixed, and there are very detailed models that people have with pages and pages of parameters within them. Okay, the takeaways is that we had this claim about what sets band spacing associated with overland flow. One could also look at something like coverage fraction, and at least in our fast flow model, there was an indication that that just tracks fairly linearly with the mean annual precipitation. So the mean annual precipitation with this typical storm strength would give you an approximate bandwidth as well as band spacing. My title has had this, it's about the water, and I just am advocating for thinking more about the water redistribution part of the problem. I know we're like drawn to the biomass and whether desertification is going to happen, and that's what we observe from the satellite images. But I think the water is what that's tracking, and that it's important to be thinking about things that are happening on that time scale. And then these questions that we're interested in, and you know, maybe there's some indication that the vegetation patterns are impacted by this sort of history of the rainfall. I got to work with great people, and we had so much fun on this, and I feel like it was a lot of adventure that went into this investigation. And so I really want to thank my collaborators, including, you know, some people that didn't get mentioned, but there's various students that I've hung out in my office with, and they just ask great questions and have great ideas. But I was particularly highlighting this collaboration with Puneet and this, you know, precursors to that, which was work with Kornegowda and Sarah Imes. And here's some references I can put up. I focused on things mainly in this paper that'll be submitted before Christmas to the archive. And then a couple of other papers. We have a book chapter and some older works that I didn't talk about. Okay, so I didn't leave much time for questions, but I'm happy to answer anything if there are any.
Sorry, I was muted. Thanks a lot, Mary. It was a really great talk. I think we have plenty of time for questions. I mean, if people want to raise their hand to ask a question, please. So maybe I can begin myself. I mean, you have shown this Floquet analysis. Mm-hmm. So we were seeing this this different band of stability or instability.
Yeah.
So does this imply that there is some kinds of multi-stability? Does it mean
there is huge multi-stability, and thank you for asking about that. I mean, that's okay. So these were these resonance bands, but even within one band, you've got this continuum of wave numbers.
Right.
Okay. And actually, when we do simulations, it's not that it always settles into like 6 bands in the domain. It'll settle into some range of bands in the domain. So it's an interesting problem, because when we if we're thinking about these collapse events, and if you think about it as, oh, okay, I have this transition from one stable state to another stable state, it could be that it just goes to a different pattern, right?
Okay.
Or it could go to the desert. But we've done experiments where we start out with, multiple bands on the domain. And it seems most of the time it just all of the bands collapse sort of simultaneously when it goes to the desert. And it was more rare that we would see like one or two bands disappear and be left with one. So yes, there's enormous multi-stability. The spacing of these here is just saying that, oh, for this bottom one, the water's traveling, from the bare region to the first band. And this one, it's like it's traveling from the bare region to the second band, and this one, the third band.
So your basic explanation is that the band spacing is related to how far the water travel. So
Right.
is there multi-stability in how far the water travel in
Well,
presence of, it's coupled to the biomass distribution, I guess.
Yeah. And it travels very slowly when it's in the biomass region, and it travels very fast when it's going over the bare region. So it's not that it's traveling, this calculation is done by perturbing about the uniform state.
Right.
Yeah. So it was from looking at this, we started to want to look at these kind of quantities. So I would say, shout out for simple models that you can do these kinds of things like this linear stability analysis, and it tells you something to look for, and I think the more complicated models, they have certainly have a role to play, but I want to just say these simple, 3 coupled PDEs that you can do some kind of analysis on, traveling wave analysis on, you get ideas of what to look for.
Okay.
We have to close the loop, of course.
Right. So
we have a hand up from Tim, if you want to unmute and ask.
Yeah, thanks. Nice talk. I was curious, I guess I want a corollary to that I was curious about would be whether you think that these more complex models, like in 2 dimensions, need to be cautious about being able to resolve the sort of largest unstable mode. If they predict a collapse, is that really necessarily the case if they're not allowing for a big enough domain?
Right. Yeah. I don't know that other people were looking at collapse in the way that we were, like the Sally Thompson paper that I was pointing out. They weren't looking at collapses there. I would say that when we were doing it, a lot of our experiments were on domains that were not terribly large. We've done runs like this one where it was a kilometer-sized domain, but others, where it's just like a few hundred meters. So yeah, so maybe I can, a couple of slides that I didn't show. These are results of, okay, so here we were varying the size of the domain and looking at collapse time. And if the domain was too small, it collapsed much more rapidly. So this is a number of years to collapse as a function of domain size, but it seemed to kind of level off. Okay, and then we've also looked at like, okay, if we change the typical storm strength, smaller storms seem to be better for it to live longer. And these are these experiments where we looked at multiple bands in the domain, and it really didn't seem to, like make a difference.
So are these collapses random events, or they are just deterministic events?
They're random events. Here are all of the data.
Right. So can you think of predicting them using I don't know, large deviation theory related to some random aspects of the dynamics?
I would love it if you could do that. I don't feel like I know how to do that. And I feel like it gets complicated because there's so many stable states, right?
Right.
You know, that I could, you know, if I take a kilometer sized domain, I could have many different, you know,
Right.
even on that, I could have many different pattern states.
And so another question
I
related
could sort of like lump those together and say that's one type of state. And I don't know what is the right kind of space to be thinking about these, you know.
So you, in your Floquet analysis, so you use a periodic forcing, a periodic spraying.
Right.
So do you have some idea for the mathematics when you have a stochastic forcing? I mean, is there any way of thinking about this mathematically?
I don't at this time know how to do that. I feel like it should be possible though. And so that was part of the reason I wanted to show that slide of the differences between the periodic. Yeah, so back here,
It's quite different indeed.
it was very different. It was just fascinating to me, like just how different it was. You know, it's really rich. And so, you know, if I think of the kind of work that people like Arjen Dolman have and his collaborators have done, where they do traveling wave analysis for these PDE problems, periodic traveling waves. If you have something that's not time dependent, that becomes easier to do. But maybe you can do some kind of averaging or something over it. You know, these aren't exactly like uniformly traveling waves, though.
Right. So I was also very intrigued by your last slide about the human impact. So do you
thank you.
Do you understand how human impacts affect by which mechanism?
So what I can tell you, this was work of this student that I had, Karna, who was amazing. And basically he was troubled by some of the early warning signs work because he felt like people really should be looking at what can be measured. So he tried to just go in completely agnostic. And so in these 9 sites, there were these 5 where this blue means there's clear signs that humans were there. Because in the 1952 image, wait, sorry, the blue ones, nothing changed. Blue means nothing changed. Sorry, let me go to the yellow ones. Yellow means things changed. And so yellow means that in 1952 photographs, there's no roads. And by roads, he means like just tracks through the landscape, like people are just taking their car and driving across it. So you see these kind of scarring in the images. And in 2015, there's dense roads. So that's, and I don't know if it's something like it's breaking up the soil crust or diverting the water into the tracks. There's some, at least anecdotally, it looks like something like that's going on because you can look at different times of the year and you'd see like grasses growing in those tracks. So maybe the water's getting diverted. The thing that was surprising to us is that where there were humans, in this case, there's a settlement that cropped up. Where there were clear signs of humans, the bands actually either disappeared or a lot of them got wider. You know, so that was surprising to us because we thought wider is better because there's more biomass. But it could be that it's a less, you know, like it's more grasses than trees. We know this is in a region where there's a lot of poverty and there's a lot of like, you know, cutting down of the trees to create charcoal to sell. So I honestly don't know. And the main thing I wanted to say here though is that the desertification could be happening because of what humans are doing, not because of the climate change. or not directly because of the climate change.
Right.
And the other thing is that you can measure things like bandwidth, and that might be changing more than band spacing.
So I know that in Sahel, in Africa, currently, desertification is occurring by a couple way by humans and the climate change, because of climate change, people are forced to change the way they do things, and then because of that, they have more impact on the vegetation. So it's initially induced by climate change, and then it is much affected by the how the people have to react to climate change.
Yeah, so and that's not in these models. And I think, you know, Karna's takeaway from this study was he tried to go in and be kind of agnostic to changes. And the thing, when he started looking at these images in detail, it was just so clear where humans had been and where they hadn't been.
So there is a further question in the chat. By Chensi Kyo, do you want to ask it directly?
Hi, I was just wondering if you've considered soil microbe interactions
I have not.
that might.
So what I would love to hear what you're thinking there.
It's not my expertise. I have a colleague who is an expert on this topic. I can maybe send you his information, but there might be an influence on the forcings just from the soil microbe interactions in the communities.
Right. Yeah, I know that. I believe that the soil microbes are important for those crusts that happen on the bare regions. So I know people have thought about that. And possibly also there's other types of vegetation patterns like these fairy circles, and there people bring in all sorts of things like termites, but also I think trying to look at the microbes. The other thing I would just mention because you mentioned soil microbes, this former student of mine, Karna, he ended up retraining kind of as a microbial ecologist because he really wanted to be able to actually do controlled experiments. So that's what he's doing now. And he wants something on a shorter time scale, like the scientist in him was frustrated by studying something that's so slow and that it's just observational, So he's been looking at soils now in a completely different career direction.
Thanks. Yeah, this is fascinating. Anyway, fascinating talk. Thanks.
Okay.
Okay. So it seems that we have no more questions. So yes, really, it was a fascinating talk. I think it was really beautiful, both from a point of view of application and mathematics. So thanks a lot, Mary.
Kind of rushed, but I hope people can at least got the broad brush of what we're trying to do.
It was excellent. Thanks a lot.
Okay, thank you.